That's why they're on there as recommended. Okay? Whether or not you do them is entirely up to you, but you need to do them, especially after you're used to doing so much homework and still struggling with the tests. Now let's not do much homework at all on the essentials. Then what do you think is going to happen? You're really going to be in trouble because you will not have had enough practice to know what to do when it comes to the test. Okay? Make sure you do some of those essential problems, or do all the essentials, but also do the recommendeds. Okay, so we are moving into our very last section of calculus notes for pre-calc class, our last section. Are you excited? Are you sad? I'm sad. I do like this. Okay, today's May 18th, starting section 2.4, rates of change. We're going to start looking at how fast or how one quantity changes in relationship to a second quantity. Let's pretend to drive from Sandburg to Lockport. And mile number, this is kind of the last two digits on the odometer in your car. At Sandburg, we're starting off at 10. I pull out of the lot at 2:30. I get to Homer Glen, like 143rd and Bell-ish, at mile 18 on the odometer at 2:46. And then I make it home to Lockport, 25, and I walk in the door at 2:56. Okay? Or pull in the driveway, actually. So I want you to find the average rate from Sandburg to Lockport. So average rate is the change in distance divided by change in time. And Sandburg to Lockport. So 25, change in distance, 25 minus 10, over change in time, 256 minus 230. $15 over 26. Okay, let's think units for a minute. Our distance was measured in miles. And what's this 26? That's minutes. Okay, let's do some dimensional analysis and convert this to something that's more recognizable to us, maybe miles per hour. So change these minutes into hours. You all know your dimensional analysis, right? There are 60 minutes in 1 hour. Okay, take out your calculator, plug on through, please, and give me that to 3 decimal places. 3 decimal places of accuracy. Nuh-uh. You did something wrong in your calculator. Yeah. I'm not sure what you did, but it's not 4 point something.
0.576.
It's not 0.576 either. I'm not sure what you're typing up on your calculator.
Right. It is the wrong thing again.
Yeah. 15 times 60 divided by 26.
0.43.
Could you? Yeah. 34.615 miles per hour. Did you get that, Rishi? I don't know what you were doing. I'm sorry? Yeah, you're okay? Okay, does that seem reasonable? Driving from here to Lockport? That you're going about 35 miles per hour average? 34. Does that mean you were driving 34 miles per hour every single instant along the way? No. At some point were you driving faster than 34? Absolutely. At some point were you driving less than 34? Yes. And at some point were you driving 0? At a stoplight, stop sign, somewhere you were not moving. Okay? All right, now you guys on your own right now, find the average rate from Homer Glen to Lockport. See if you can do this one without a calculator, please. Please tell me you could do this on your calculator. Or do duh. Yes, absolutely, you can do that in a calculator. No, you can. Please tell me you can do that without a calculator. That you can divide 60 divided by 10 evenly and get 6. And then you can multiply 7 times 6 in your head and get 42. Oh, God. Look at that. 7 times 6. Oh, my. I know, it's brutal. It's brutal. Try and use your brain as much as possible. Use your calculator for the tough ones, but use your brain. You start to lose that mental quickness if you always are reaching for your calculator. How many times have you reached for a calculator to multiply 10 times 6? Oh, you have. I know you have. Some point you have. I've seen you do it. 10 times 6. People have. When your calculator's sitting there, you're not even thinking about it, and you're going. Okay, now, does this seem reasonable to you, though, that going from Homerland to Lockport, the average rate is faster than going from Sandburg to Lockport? Does that seem reasonable to you? Why? Yeah, there's going to be fewer stoplights. There are fewer stoplights going from like 143rd and Bell out to Lockport, okay, as opposed to going from Sandburg to 143rd and Bell. There's stoplights, there's traffic, there's all kinds of stuff going on. So absolutely, it makes sense that we should be going faster the second half because there's less traffic, less stoplights. What does that tell you about your average rate from Sandburg to Homerland? It's got to be less than that overall average. Doesn't that make sense? Okay. All right. Now, this is a very specific example. We can talk about average rate of change of any function, not just distance versus time, on an interval from A to B, and that average rate of change is the change in y value divided by the change in x value, or f of b minus f of a all over b minus a. We don't usually think of this as average rate of change. How do we always think of this? This is slope. Yep. Average rate of change is slope. Average rate of change is slope. Okay. Now, one of the things that becomes very, very important in calculus is slope of a tangent line. I need you to get some colored pencils and a ruler, please.
So does that mean that there is a big slope from Sandburg to Lockport?
Yes.
Which way do you take them when you go?
I go 131st to Archer, though.
I hate Archer.
Do you?
I hate it. It's the only street that's ever confused me. It's an angle street, and I got lost the first time. I am so good at directions and figuring out the only street that has ever, like, I'm pretty good on most angle streets. Like, I can't hate Archer.
Me and my friend, one day we were driving, and he's like, I don't want to stop at any red lights. So we went, and we took a right-hand turn, and we ended up on Southwest Highway. And
Yeah.
we forgot that it doesn't, that it crosses. You have to go all the way to 143rd, and it goes back.
It goes backwards.
We forgot about that whole, like, area. Like,
Okay. Do you remember tangent lines from geometry? Do you remember tangent lines from geometry? Tangent line just touches the edge of a circle. It intersects that circle at one point. That's a tangent line. It skates right along the edge of that circle. Do you recall that? Okay. Curves can have tangent lines as well. There are an infinite number of tangent lines along this curve. One of them might be right here. It kind of skates right along the edge of that curve. Here's a tangent line. And like we had in geometry, the point where the tangent line intersects that curve is the point of tangent C. We do have one difference with tangent lines, though, in on functions as opposed to tangent lines on circles. This tangent line will never intersect this circle anywhere else except at that point of tangent C. However, on curves, we can have a tangent line intersect the function at other places. This is a tangent line, but it's only tangent right here at that point of tangency. Okay, we did intersect this curve over here, but that is not a point of tangency. And it has to do with that line kind of skating or skimming right along the edge of that curve. Do you see how this line skates right along the edge here, but not here? It kind of crosses directly through. Crosses directly through over here. Visually, do you see the difference between where it's tangent and where it's not? Yeah? Okay. We are very, very interested in the tangent lines to a curve. Very interested in finding the slope of these tangent lines to a function at a given point. So we're going to go here, and I want you to consider this function, y equals f of x, on this interval from a to b. And the first thing that I want you to do is I want you to find, take that a and line it up to the function, and then carry that over to the y value, and that y value would be f of a. This b, pull it up to the function, carry it over, and that's f of b. Would you agree with me that the coordinates of this point right here on the function at a are a comma f of a? What's the coordinates right here? You gotta look. What's the coordinates here? B comma f of b. Everybody okay? Alright, now I need you to go back to geometry for a moment. Go back to your circle that's on the other side. Go back to this circle down here. There was a tangent line. Do you remember what a secant line is? Crosses at 2 points, exactly. So here's a secant. There's a secant line in geometry. Okay, now on this function, I want you to draw the secant line between these 2 points. Draw the secant between a f of a and b f of b. There's the secant. And I want you to draw the tangent line at A. Tangent line at A. So again, the line has to skate right along the edge. Alright? Okay, now look at the slope of the secant and the slope of the tangent. They're both positive slopes? Both positive, but the slopes are different right now. Correct? Different slopes right now, both positive but different slopes. Alright, looking at this picture, could you write an expression for the slope of the secant line? You write an expression for the slope of the secant, Manish, what would it be? Exactly, f of b minus f of a all over b minus a. Okay, I want to make some adjustments here. Between this a and this b, could I label this distance as some amount, call it h? Then, could I rename this b? And instead of calling it b, could I call it a plus h? Does that make sense? But that b is a plus h. Okay, now let's make those substitutions. So b is now a plus h. So we have f of a plus h minus f of a all over b, which is a plus h minus a. What happens? In the denominator, what happens? The a's cancel out, and this is called f of a plus h minus f of a all over h. Yes? So far? Does that look familiar? Okay, this is called standard difference quotient. We did this earlier this year in the first chapter, and when I gave these to you, I said, here, evaluate this standard difference quotient. I never really told you what it was for, why we did it. It was just a precursor to calculus. Well, now here's where it comes into play and why it's important and what it all means. Okay, so now don't do this on your notes because it's going to get very, very crowded in here, and I don't want you to mess up your notes, but I want you to watch this. My h right now is pretty big. What if I made h smaller and I put b right there? Then that point would be here, or b, f of b would be there. And when I drew in the secant line, I would get this line. Okay. Well, what if I made h smaller yet? And I put h maybe right here. Then, when I draw in my secant line, it's there. Okay? If I make h smaller still, what's happening? It's getting closer to the tangent. Yep, that secant line is kind of narrowing down, and it's going to be in here. What about the slope of each of those secants? As I made my h get smaller and smaller and smaller, what's happening to the slope of the secant line in relationship to the slope of the tangent line? It's getting, the slope of the secant is getting closer and closer and closer to the slope of the tangent. Okay, how small can we, and that happens as I let h get smaller and smaller and smaller. Well, how small can we let h go? Can h equal 0? No, h can't equal 0 because then I wouldn't be able to figure out this actual slope. But can I let h get very, 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 very close to 0? Yes, we can. And what's that called when we do that? A limit. When we let h approach 0 of f of a plus h minus f of a all over h, that is the slope of the tangent line. I should say slope of the tangent line at x equals a. Yes, you need to memorize this. Slope of the tangent line at that point, x equals a, is the limit as h approaches 0 of f of a plus h minus f of a all over h. Okay? Alright, let's plug through a problem and see how it works here. given that y equals x squared minus 4x, so there's your function. I want you to find the slope of the tangent line when x is equal to 1. This x equals 1, that is the a value. That is where the tangent line is occurring, or where it is tangent, the point of tangency. Okay, the slope of the tangent is going to be the limit as h approaches 0, f of a plus h minus f of a all over h. I just wrote the formula. Now I'm going to substitute in. We know that a is 1, so f of 1 plus h minus f of 1 all over h. Okay? Alright, now, here's this function, x squared minus 4x. What if I wanted you to find f of 5? What would you do? Plug in 5, right? Well, I want you to find the function evaluated at 1 plus h. So we're going to put a 1 plus h in for that x. We have the limit as h approaches 0 of 1 plus h squared minus 4 times a 1 plus h. Everybody okay? Minus f of 1. What do you get in that function when you plug in a 1? Say it out loud. What do you get? Negative 3? So minus a negative 3 all over h. Okay, can you evaluate this limit right now? How do you evaluate a limit? You substitute in. Can you sub in at h equals 0 right now? No, we're in trouble, so we're going to have to simplify. You square this out for us and distribute that minus 4 through. Anybody volunteer want to square that out and distribute the minus 4 through? Sharad? Keep going. Plus 3, right? All over h. Alright guys, what happens? I'm sorry? Everything without an h drops, absolutely. There's 1, negative 4, and there's 3. Those subtract out to 0. So we're left with, oh, I'm running out of space. I'm going to have to come up over here. The limit as h approaches 0 of, we have an h squared minus a 2h all over h. Now what do you see? You can take an h out of everything, which leaves us with h minus 2. Alright, when we wanted to evaluate this limit, what was causing the problem? The h that was in the denominator, right? Because that was a 0 in the denominator. Have we gotten rid of that h problem in the denominator? Yeah, so now can you substitute in 0? We can substitute in 0 and we get negative 2. Alright, what is that? That is the slope of the tangent at x equals 1. That's the slope of the tangent line at x equals 1. Yeah? Nicole?
What did you do to get 1 plus h squared minus 4?
This one?
Yeah.
Okay, right here I took, this is f of 1 plus h. So I'm taking the 1 plus h and I'm plugging it up into the f of x function everywhere you see it in x. Does that make sense? Okay. Manish? Because that's the goal of this, is to find the slope of the tangent line. So I wanted you to see that initially the secant line, which we could find the slope of, that was not the same as the tangent line. But if I made this distance between these 2 points get smaller and smaller and smaller, that the slope of the secant gradually got closer and closer and closer to the slope of the tangent line. So that was our goal, was to find the slope of the tangent line. Does that make sense? Yeah? Okay, so now, it's a continuation on this very same problem. I want you to write the equation of the tangent line described in number 1. So write the equation of that line. Anytime you write the equation of a tangent line, and you're going to be doing this until you're blue in the face, you're going to write tons of equations of tangent lines. Always use point slope form. Y minus y sub 1 is m times x minus x sub 1. M is slope. We just figured that out. What was the slope? -2. X sub 1, that's the x coordinate of the point of tangency. I told you that initially. That was at 1. And this y minus y sub 1 is the y coordinate for the point of tangency. So that's just taking this x coordinate 1 and plugging it into the original function, which we did already when we did f of 1 on the previous page. Are you with me? What was that? -3. So this is y minus the -3. And we'll simplify this down to be y plus 3 equals -2 times an x minus 1. You do not have to put that into slope-intercept form. It's perfectly acceptable to leave your answer in point-slope form. As a matter of fact, I prefer you leave it in point-slope form. Okay? All right, next part. In all of these are all right up, they're all related to this problem that we just did. I want you to write the equation of a normal line to the tangent in 1 and 2. And a normal line is a line that is perpendicular to the tangent at the point of tangency. It's at the same point. So point slope part, that the x sub 1 and the y sub 1 remain exactly the same. The only thing that changes when you're going from a tangent to a normal is the slope. What do you know about slopes of perpendicular lines? Opposite reciprocals. So if the slope of the tangent is -2, then the slope of the normal is a half. Okay, so far? All right, grab your calculator, please. Anybody need to borrow a calculator for today? Okay, I want to show you some things in your calculator. I think we've talked about this before, but I'm not sure, and I just want to show you a couple of things. So, y1, put that in as the original function. Oops. X squared minus 4x. Okay. y2, we're going to put the tangent line in. Now, instead of you doing the arithmetic and maneuvering this equation around to be point slope form, start putting it in as written. So look what I have. -2 times an x minus 1. Can you see it? And then I just took that plus 3 that was on the left side and I just moved it over to the other side as a -3. That way you're letting your calculator do the arithmetic. Does that make sense? for this one, it's not that much trouble to put it into point slope or into slope intercept, but can you imagine if you had icky slopes and icky points, how difficult that would be? So let your calculator do the work for you. Likewise, with the normal line, I went ahead and did the same thing. So 0.5, x minus 1, and then I just took that plus 3 and I moved it over. Okay, please go ahead and graph this on a standard viewing window, so zoom 6. There's the function, there's the tangent line. See how that tangent line just skates right along the edge of that curve? And there's your normal coming through. Everybody with me? Okay, we have a problem. We have a problem because our normal line is supposed to be perpendicular to the tangent. Is it? Certainly doesn't look like it. Here's a piece of paper, right? Right angles. And if I take my paper and I line it right up along this normal, there is no way that that is going to be perpendicular to the to that tangent. Do you see what I'm saying? Why? Why? Because why what? No, it isn't the point of tangency. It just doesn't look like a right angle. How come? Because why? The window is not square. We're on a square window right now, right? Do you remember that the ratio of the x to the y is roughly 3 to 2? 3 to 2. So if you change your x's to be negative 9 to 9 and your y's negative 6 to 6, that's a ratio 3 to 2. Now graph the parabola looks the same, but what's going to happen is the perspective, or there's the tangent, there's the normal. Now do they look perpendicular to each other? Absolutely, they do, and it fits that corner. Does that make sense? Yeah? Okay, I do want to do one more thing before you go, and that is that I do want to get an accurate graph drawn on paper. So, and if you just number off your grid, just to make it a bit more accurate, I'm marking off every centimeter. Can you read the zeros off of your parabola? Off your graph? Either off the graph or by looking at the equation. You should be able to tell me the zeros pretty quickly. 0 and 4. Vertex is halfway in between, so it's going to happen at x is 2. When I plug that x equals 2 into the original function, we'll get 4 minus 8, which is negative 4. Tangent line. We know that our point of tangency was 1, negative 3. And the slope of the tangent was negative 2. So I can plot that point and just count a slope from here. Up 1, up 2, backwards 1. Up 2, backwards 1. And the normal, same point of tangency. Slope is a positive half. And when you put those in, you absolutely should see perpendicular lines here. Here's the normal. And we do have right angles in here. Are we good? Okay, all right. Anna was sick today. She emailed me this morning and asked me to video this for her. Wasn't that smart? So you guys, do you see the little green in the corners down here? That's because I'm recording you. Did you notice?